Okay, people, so before the exam we started talking about this stereo chapter, and I think we talked about what stereo is. We talked about the derivation of the disparity formulas, and we talked about these anaglyph images, and we said that human beings, they understand depth both from the cues, the depth cues such as the sizes of the objects and the vanishing points and the occlusion, etc. Also, we said that our left and right eyes are useful for inferring depth even from the nonsense images like these random dust stereograms. We talked about those, and then we know this formula already. We derived it. We said that the depth of a point z depends on the disparity of the point and the baseline between the cameras and the focal length of the whole system. The baseline is, of course, the length of this distance. The distance is between the central projections, okay, of the two cameras. That's the baseline. And focal length is, of course, the focal length of these two cameras. And the disparity is again the positional difference of the same point in two cameras. So that's the formula. We said that increase the disparity, depth will get smaller, so the point is close to the camera. Lower the disparity, z will grow. That's what we said. We talked about these, and then we started talking about epipolar geometry, and I think I left around this point. So let's start from this point. Any questions up to this point about stereo? So epipolar geometry says that if you have two cameras, pi and pi prime, two cameras looking at the same object p in the real world, one of them will see this p as small p, like this. The other one will see this p as p prime, okay? And looking at this geometry, we say that there is a surface, there is a plane that goes through these 3 points. The point P in the real world, the central projection of the left camera, and central projection of the right camera. Okay? So two cameras and 3 points. We say that this is a plane, and we call this plane epipolar plane. Why is this plane important? This plane is important because I know that to solve the correspondence problem, I mean to say that P corresponds to this P prime, or let me show you one, yeah, to say that this P here that corresponds to this P prime, I need to make a search. Take this point P on the left image, on the right image you need to make a search, okay? And among all the points, you are going to say this is the point that matches the best. And the epipolar geometry says that you are going to make this search on a single line, not on the whole image. So your line might look like this. So on this line, you are going to make a search, and I am trying to get this line. When you look at this epipolar geometry picture, okay, to search for this P on this pi prime plane, you say that, okay, this P could be either here or there. Use a different color. Either here or there, or there or there, okay, like this, anywhere on this line. Well, I mean, if I take the picture of this line, it would be this line. Let me draw it with red. It would be this line, right? Okay, here. It would be this line. So to find the corresponding point to this P, I need to search for the solution, search for the correspondence on this red line, and I am going to try to find what that red line is. That's mathematically, okay? That's what we are going to do. So to do that, I need to make some definitions, and my formulas will depend on it. So this plane is the epipolar plane, and for this P, I have a line to make a search. Okay, that's the line to make a search. Also for this P prime, there is a line to search. This is L. This L and L prime are called conjugated epipolar lines. Okay, these 2 points are special, E and E prime. The line that connects O and O prime goes through these image planes, E and E prime, and they are called epipoles. Okay, E and E prime are called epipoles. Then I have the baseline. Baseline is this vector between O and O prime. Okay, E and E prime are special because if I move P around, let's say I have moved P here. Okay, so I will have a new, let me use a different color, maybe red. I have a new epipolar plane. Okay, this P prime will be here, this one will be there, maybe, right? Okay, and the conjugated epipolar lines will be, in this case, this one and this one. Okay, so I have a new two conjugated epipolar lines. Maybe I shouldn't make it so big, just make it like this and make it like that. Okay, so conjugated epipolar lines are now this, but whatever you do, wherever you move your point P, there its conjugated epipolar lines has to go through this E and E prime. That's why those are special. Those are called epipoles. Okay, so this is epipolar geometry. These are the definitions. It all plays around this plane, this simple plane. That plane goes through this point P, O and O prime. O and O prime doesn't change for the given scene, but any point on the scene, of course, will produce a different epipolar plane. Okay, we already looked at this one. Okay, let's move on. Let's look at this. Last time we talked about this, right? We said that if, okay, let me make it a little bit smaller so that I can fit both of them. Okay, we said that if these 3 points are on a plane, then if I take two vectors, vector number 1, this vector, okay, and vector number 2 is this vector here, and the vector number 3 is let me use the green. Green is not a very good color here, but this vector. Okay, so I have 3 vectors. If I cross product these 2 vectors, if I take a cross product of this red vector with the green vector, okay, red vector with the green vector, then I will get a new vector that is perpendicular to this plane. Okay, will be perpendicular to this plane. If I take a dot product between this blue vector with this new vector, it will be 0, because if two things are perpendicular, if two vectors are perpendicular to each other, the dot product between them will be 0. That's the definition of the dot product. Okay, so that's what I'm going to do. Here is what I'm doing. Take the O prime, that is the red vector. Okay, this is the red vector, and cross product it with the green one. Okay, and then I am going to dot product it with the OP. Okay, so this is O prime, this is O prime O prime P prime, and this is OP. Okay, that's what I have. This I get C. This is important because once we get 0 at one of the sides of the equation, then I can do many things. I can take advantage of it. So I know that using this equation, I will try to get given P, okay, given for example this P here, what is the corresponding conjugated epipolar line in the other image? I'm trying to produce such a line. So if somebody gives me this P, I will produce a line formula for this P prime. Or if somebody gives me this P prime, I will produce a line formula for this P. Okay, that's what I am going to do. Okay, so let's do this. But before going further, cross product. Well, dot product is like a matrix multiplication, right? With the dot product, you do this. Okay, you are given a vector like this one, another vector. I take this vector. It has 3 components in it. Take the transpose of it. Now I have this vector. Okay, transpose vector. If I do the matrix multiplication between these two vectors, a column vector and a row vector, I can do the cross product, but this is the dot product, sorry. But for this cross product, I need to do something. I like to linearize it. People came up with this idea. They say that this is the regular way of doing the cross product between two vectors A and B. Okay. If the vector A is A1, A2, A3, vector B is B1, B2, B3, then the cross product between two is taken like that. Okay. Take the determinant of this part. Okay, A2, A3, this part times I. Okay, it will go here, and then take the determinant of this part. It will go here, and take the determinant of this part. It will go here, and there is a minus sign there, right? We know this from high school. We know this from high school. People say that instead of doing this, I can do this in a linear way, in a matrix multiplication way. If you are going to take the cross product of A and B vectors, convert A to skew symmetric matrix form. Skew symmetric matrix form. Like this. But it's a symmetric matrix. So A3, A3, A2, A2, A1, and A1. But it is not perfectly symmetric. It is skew symmetric. So what is the meaning of it? It is minus here, minus there, and minus there. Okay. So if you represent A as a cross-productable way, okay, cross-product representation of A, I will say A3, A3, A2, A2, A1, A1, and minuses are there. So what did I achieve? If I do this matrix multiplication, I am doing the cross product. That's nice. Okay, that's nice. So I am going to use this idea here. I am going to take this vector, convert it to a cross product version of it, and multiply it with this vector. That's what I am going to do. And this is already a vector. So what is this vector actually? OP is actually in the camera reference frame. O2 is actually this vector. It's just P. So this is 0, 0, 0, right? This is 0, 0, 0. What is the position of this small p? Okay, it is P's position. So P has 3 components, X, Y, and Z components. Its Z component is F. It is still a three-dimensional point. So it is just P. Okay, so if this is 0, 0, 0, this is P. If this is 0, 0, 0, this is P prime. Okay, I know that. Okay, so this one, in this case, O prime, P prime is P prime. This is P, but their coordinate systems are different. Okay, this one lives in a different coordinate system. This one lives in a different coordinate system. So maybe I should translate this O prime, P prime to this coordinate system. What am I going to do? I will take this baseline T, O prime, right? subtract it from this point, and rotate it with rotation matrix. So I need this translation vector between these two cameras and a rotation matrix to rotate the point from the right coordinate system to the left coordinate system. Okay, that's what I'm going to do, and that's what these guys are doing actually. So I'll say that this T is the of course this baseline. I am going to represent this T as a cross product version of it, okay? As a cross product version of a skew symmetric representation of T. P is already what I know. R times P prime is the rotated version of this. R times P prime is the rotated version of this point here, rotated version. You are going to say, what happened to this baseline? I mean, I had the baseline in it. Well, I mean, doesn't matter where this vector lives, okay? Its initial point is. The important thing is its orientation. I mean, with the rotation you are changing the orientation. Orientation is important, but translation is not important for the cross product. Because I am trying to simply produce a perpendicular vector. So, in terms of camera coordinate system notation, P times, okay, this is the cross product, dot product, T cross product R P prime is my thing, is equal to 0. Okay, I still did not use the skew symmetric version of this T. That's what I am going to do now. Okay, so I say that if I take this, okay, and if I represent T as an skew symmetric version of it, and if I multiply it, what is the size of this Tx? What kind of matrix is this? How many by how many? 3 by 3. What is the size of R? Rotation matrix? It is 3 by 3 again, right? So this is 3 by 3. This is 3 by 3. If I multiply them, I will get a 3 by 3 matrix, right? So this is this matrix. If you multiply this matrix with this one, this matrix is called essential matrix. And given 2 points that can correspond to each other on the left and right images, if you multiply them with the essential matrix in the middle, you will get a 0. If somebody gives you a P, okay, if they tell you that this is your P, this is your essential matrix, then you have a formula for P prime. You cannot solve P prime because you didn't solve the correspondence problem yet. This will only tell you, okay, let's say this is your left image and right image. This is your P, and they gave you the essential matrix too. Writing this formula, P times essential matrix times P prime, I know this P, I know the essential matrix, equals 0. So this has 3 components, right? You are going to get something like AX plus BY plus C is equal to 0. Okay? And it will be a line in the other image like this. So that line is the line that where you are going to make a search. Where you are going to make a search on the image. Okay? So this is what we came up with, starting from the assumptions of the epipolar geometry, the epipolar plane. Plane gave us this formula. From this formula, using our camera parameters and etc., using the baseline vector and the rotation matrix, I came up with this, and representing T as a skew symmetric version, I write this formula. Okay, and since I like to be in the linear algebra world, I say that take the transpose of P. Okay, so P is a vector, make it a row vector. Okay, so it's a row vector now. I have to take this. Dersteyim. Alo. Dersteyim. Acil mi? Dersineyim, çıkınca ararım. Take this. Okay, let me try to. Okay, take this P, represent it as a row vector, 1, 2, 3 elements in it. Okay, and get our essential matrix, 9 elements in it, and the other P is of course like this. It has 1, 2, 3 elements in it, and it equals 0. That's the formula. Okay. Good.
Tibis'te kaydı açmamışsınız. Arkadaşlar bir yandan yazdı da. Tibis'te sizi takip eden arkadaşlar vardı. Acaba paylaşacak mısınız diye soruyorlardı.
Yok, ben internete giremiyorum buradan, denedim. İnternete giremiyorum. Ağlama dersin başına. İnternet yok. Okay. So this is good. This is nice. When we have such a nice equation, I can come up with the lines for the other side of the stereo pair. That's what we know. But the thing is that this essential matrix works for the points in the camera coordinate system. Camera coordinate system is nice, but it is not as nice as the image coordinate system, because given an image, I know it's row and column. Okay, so I know that in this image, the second row and the third column of this image is my point, you would say, for the image coordinate system. In the camera coordinate system, it doesn't work that way. Why it doesn't work that way? Because in camera coordinate system, we are talking about in millimeters. We are talking about in, okay, if this is 0, 0, 0, then my point is here, and etc. That's not a good thing, because most of the time I don't know what my camera coordinate system points are. Okay, so what am I gonna do now? Then in that case, essential matrix is nice, but I need to do something to make it work with the image coordinate system, and I will come to that one in a few minutes. So here is the essential matrix. It is shown with this letter E. It is essential matrix. It has 9 coefficients, but it is only defined. Can anybody tell me what this is? It has 9 coefficients in it. It's 9 values in it, but it is only defined up to a scale. If I give you an essential matrix like this one, I can multiply this essential matrix with a K, and it would be another essential matrix, and it would work on this one. Why? Because I can multiply both sides with K, right? Because it has 0 on both sides. So there is no unique. You cannot say that I have a unique essential matrix, because there are infinitely many essential matrices, but they all depend on each other with a scale, K. Okay, and inside essential matrix, actually what you have is, inside the essential matrix is what you have is actually this. A baseline vector and a rotation vector. A baseline vector has 3 components at x, y, z, but the important thing here is with the baseline is its direction. So 2 numbers from here and 3 rotations around x, y, and z here. Okay, so total of 5. Okay, 3 degrees of freedom for the rotation and 2 degrees of the freedom defining the direction of the translation vector. Okay, so the total of 5 numbers defines these 9 coefficients. Okay, so how do I write the line resistance in that way? So if somebody gives me this one or that one, that one gives me automatically a line formula. essential matrix is nice. But as I said, it is not as nice as a formula that works on the image coordinates, and that's what we are going to say. So how do you connect, let's say P hat is in our image camera coordinate system, and I like to get to the image coordinate system P. How do you get from this P hat to P? P hat is in my camera coordinate system, P is in my image coordinate system. How do you convert this P hat to P? Come on, yes. Last week we had our midterm exam. I mean, you're supposed to know this. Say it louder.
We can use homogeneous coordinate system.
This is already in homogeneous coordinate system, yeah.
So we can divide it to the last coordinate.
No. Well, this is in millimeters and this is an image coordinate system. This is in millimeters. This is an image coordinate system. This one talks about 3.4 x value, 2.1 y value, and 31.0 f z value. And this one says third column and fifth row.
Not we have scale in our intrinsic parameters.
So how do you do that? I mean, we already solved this problem. You multiply it with matrix K, remember? Our intrinsic parameters. This is a 3 by 3 matrix that includes our the width of the pixel size, okay, the height of the pixel, also our skew angle if we have any, principal point of the image, and etc. This is a 3 by 3 matrix. If I multiply this P hat with K, then I will get P. Well, let's say these are P hat and P hat prime. So maybe instead of P hat, I can say P hat is equal to K to the minus 1 P, right? Good, I can write it. Also, P prime hat is equal to K prime minus 1 and K prime minus 1 and P prime. I can say that, okay? So instead of writing P that way, let's write it that way, okay? So it's going to be K minus 1 times P, of course, transpose, times for the P prime hat, I will have K prime minus 1 and P prime, right? So how do you take the transpose of this thing? Do you guys remember? If you have two matrices A times B, how do you take the transpose of it? From linear algebra? You don't remember? Okay. It is this way, okay? B transpose times A transpose. Then I will write this. Let me make this a little bit smaller so that it can fit. Using the same equation, I will say P T times K minus T. We represent it this way. It's like transpose and inverse of it, times E times K prime minus 1 and P minus 1. This is 3 by 3, right? How about our K matrix? What is the size of our K? It is 3 by 3 again, and this one is 3 by 3 again. So if I multiply these three if I multiply these three matrices, I get a new matrix, and it is called fundamental matrix. And fundamental matrix is shown as k minus t times essential matrix k prime minus 1, just the inverse of the k prime. So this is the intrinsic parameters of the left image and intrinsic parameters of the right image. Okay, that's what it is. That's called the fundamental matrix, and this is how we do the fundamental matrix. Okay, the nice thing about fundamental matrix is now this p and p prime, they are in image coordinate system. Okay, they are in image coordinate system. Now we are talking about third row and fifth column and etc. in homogeneous coordinate system, of course. So I can definitely say, given two images, if they give me this F matrix, 3 by 3 matrix, then I can calculate the line to make a search on the other image. Okay, so this is called the fundamental matrix, and inside the fundamental matrix you have the essential matrix. Essential matrix has inside the head 5 parameters. Remember, rotation plus the 2 degrees of freedom for the direction. And inside this F now I have this K and the other K, many numbers, but it looks like this F matrix, fundamental matrix, is not a full rank matrix. It is not rank of 3. It is determinant is not determinant is not it is not a full matrix. You cannot solve this F like a regular matrix. Its rank is not 3, its rank is just 2. So that's why we say it is at most 7 degrees of freedom. There are proofs of it, but I am not going to go into that one. But that's a very useful matrix. For a given 2 camera looking at the same scene, you can calculate this fundamental matrix, and that's going to be very useful. Or if you have 2 fully calibrated cameras, then you know the t vector, tx, you know the r, you know the left and right k values, then you are fine. You know your f. But usually we don't do the camera calibration to calculate the f. Instead, we do weak calibration. Okay, so on my left image I have uv, and since I'm in homogeneous coordinates I put a 1 in there. On my right image I have u prime, v prime, and I have put a 1 in there. Okay, if I have 2 images like this, and I know that this point 1 corresponds to this point 1 here, okay, and this point 2 corresponds to this point 2 here, this point 3 corresponds to this point 3 here. I know that if I know the correspondences in before, okay, I can write this UV values. Each correspondence will give me an equation of 0, right? So I multiply this with this matrix and then this one. It will give me information about these numbers. So if I have enough number of correspondences between these two images, then I can calculate this f11 to f33. Okay, and that's how I can calculate this fundamental matrix F. That's called weak calibration. Why is it weak? It is weak because I am not calculating any intrinsic parameters, or anything. I'm just calculating these F values. Once I have the F values, I can draw my lines. This fundamental matrix, its name is fundamental. It is crucial to the stereo calculations. That's why people like it a lot. That's why people sang songs about it. In fact, I am connected to the internet now. Okay, let me go. How did it happen? Where am I? Okay, I'm connected. So let me go to YouTube, and there is a fundamental matrix song. Really? Okay. Fundamental matrix. Yeah, here it is. So and more than 100,000 people saw it. Do you guys, oh, you can't hear it because it is not okay. Okay, start from the beginning. Just 3 minutes.
You ready? Yes, yes, right, we're recording. Okay, go. The fundamental matrix used in stereo geometry. A matrix with 9 entries. It's square with size 3 by 3.
Usually they define these, they have the definition for each of these values in 3 by 3. I am not going to go into that detail, but I mean, if you like to go into the details, you can make sense out of it. It says A, B, C, D, E, F. These are dependent on these 6 values, okay? And I have alpha and beta, total of 6 and 7, 8 numbers.
7 degrees of freedom. It has a rank deficiency. It's only of rank 2.
Its rank is 2, we already know that. This information is important because when we calculate the fundamental matrix, we will say that I should get something of rank 2, not 3, not 1, just 2. So that's important.
Pull a matrix F and you'll see 2 points that correspond. Column vectors code x and x prime. X prime transpose times f times x equals 0 every time. The epipolar constraint involves that epolar lines. Those multiplying f by x results in vector L prime. It's the epipolar.
Now he is talking about the epipoles. Remember the epipoles, they are important. If you solve this fundamental matrix like f x 0, okay, you are going to get one value of e, okay, for this one, and that e is your epipole for one of the images. Why? Because doesn't matter if you can satisfy this equation. If you can satisfy this equation for x value, doesn't matter where you put anything in here, p, right? Doesn't matter what p is, because I can already satisfy this fx is equal to 0. That means what? X is a corresponding point, can be a corresponding point for any p on the other side, right? So if you solve this one, fx 0, okay, this x is going to be your epipole for one of the images. That's what it says in this case.
Homogeneous design. The left and right null spaces of F are the epipoles E prime
Null
and
space of
T.
f and ft, yeah.
The epipolar lines should pass through these. Is a linear estimation except.
So now he is doing some exercise now. On this left and right image, I think he will have 2 images. So this is the second image. First image, okay. This is the first image. This is the second image. Okay, he got 8 of them. And I didn't talk to you about left image and right image. These are two different images, you see that, right? So this is a stereo pair. He is tracking the tip of the bow, the violin bow, okay? He has X and Y. He has X and Y coordinates for this bow, and he's going to calculate. See, he's drawing the epipolar lines. If you are going to make a search for this dot on the other image, you'll have to do it on this line. And every time the point changes, of course, the epipolar line changes.
Here we go. We try to estimate.
Anyway, so you watch it later. And as I said, it's so important that we have a song for it. It's called weak calibration. And as I said before, if you get many correspondences between left and right images, if you get it somehow, how do you get the correspondences from left and right images? You do this. You take the image of a checkerboard, right? You take an image of a checkerboard. On your left image, this is your checkerboard. On your right image, this is the same checkerboard, like this. And ask Opencv to find the checkerboards for you. Opencv will tell you that, okay, I found the corners. These are my corners, and the same corners are here again. Opencv will give you the correspondences between these corners and the many other corners too. So you have many correspondences between left and right image. Once you have those correspondences, you write all of them, okay? You write all of them, and each correspondence will give you an equation about these f values, and you can get a nice matrix representation like this for each correspondence. And if you put them one after the other like a matrix, like in this form, okay, so 1 2 3 4 5 6 7 8 8 rows, it will be enough. 8 correspondences will be enough, and you multiply this with this f values, 8 of them. And why don't I have, well, the thing is this, since there is a 0 here, I am trying to find these numbers, right? I am trying to find these numbers. There is a 0 here. Whatever number you find, I multiply all of them with k. It will be another fundamental matrix. There is no single fundamental matrix for a given camera. So I am saying that if that's the case, I am going to change my f33 to 1. Now all the other values has to be unique, because I divided rest of them with f33. Okay, so I get rid of this f33. Now I have 8 rows and 8 unknowns, and -1 comes from this f33. Okay, so solve this one. Solve this matrix. Get 8 correspondences. Solve this matrix. Okay, solve this matrix, and that will give you your fundamental matrix. Okay, without doing any calibration, without doing any explicit calibration, without doing any other things, get just these correspondences and get your fundamental matrix, and it will work in the image coordinate system, and it will be fine. Okay, good. Any questions? Yes.
Where do we use Epipolar Geometry specifically?
Where do we use?
Yes.
Where do we use what?
Epipolar Geometry specifically.
Fundamental matrix?
Yes.
Well, as I said, as these guys do, okay, what did I do? Okay, you use the fundamental matrix to, if you know the fundamental matrix, okay, somebody gave you this P, you multiply this P with F, okay? And on the other side you have the P prime, right? You will get a formula, a line formula for P prime. And that line formula, we draw a line on the other image, and you will make your search on this line, not on the whole image, but on a line only. So that will constrain your search space a lot. Okay.
So do you use word processing or other subtasks of other things?
Before making a search, you use your fundamental matrix, yes. Okay, so that's the fundamental matrix, and where did I go? Okay. That's how we calculate it. Opencv has lots of help, lots of tools about fundamental matrix. Okay, one of them is, for example, calculate. Okay. Calculate the essential matrix from R and T. Remember the R and T, T cross product R. You can calculate essential matrix if somebody gives me the R value, the rotation between the two cameras, and the T value, okay, between two. Well, better yet, if somebody gives you, I have two cameras. Camera number one is like this, looking at the scene, and the camera number two is looking at the scene like that, okay? If somebody calculates the rotation and the translation vector for this camera, and again, rotation and the translation parameters for this camera, if you give me these two, okay, the rotation, okay, rotation for the camera 1, rotation for the camera 2, translation for the camera 1 and translation for the camera 2, I will give you the essential matrix. Okay? They can calculate this. That's nice. If you have the essential matrix, and if you give me your two intrinsic parameters, okay, I can calculate the fundamental matrix that way. That's the second one, calculation of the fundamental matrix. What else? And if you have the fundamental matrix, I can give you the essential matrix. Fundamental from projections. If you have two projections, for left camera projection and right camera projection, I can calculate the fundamental. What else? Yeah, this one is good. If you give me correspondences of the left and right image here, you have two images, you have many points on the left, and you have many points on the right. They correspond to each other. Give me those points, I am going to calculate this fundamental matrix using this method. Okay? So that's a good one. Normalized 8-point solver. And projections from the fundamental matrix. That is just doing the opposite of fundamental from projections. Okay, so Opencv supports this fundamental matrix idea using many functions. Okay, any questions so far? Okay, if there are no questions, let me take 15 minutes of break. Okay, let's be here around 15:38. Okay, 10 minutes. Ders arasında vereceğim. Okay, so these are the functions. There are some when we come to the motion chapter, when we talk about the motion, well, we assume that these two cameras are looking at the same scene at the same time. But what happens if I take this image at time t0 and if I take this image at time t1? So it looks like a stereo pair, right? If the scene did not change, if I change my camera position only, so it looks like a stereo pair. So I am going to use this idea of fundamental matrix or the essential matrix in the motion chapter 2. That's why we have a number of functions about motion and fundamental matrix and etc. We will come to those when the time comes about motion. Okay, so let's move on. Wait. So we are now going to look at this reconstruction problem. Reconstruction problem is this. You have achieved somehow the correspondence. You know that this point P corresponds to point P prime. I know that, but P and P prime, they correspond to each other, but the way I found this is noisy. Why? Because it depends on my camera calibration, because it depends, after all, I am looking at the pixel values. I mean, in the image coordinate system, I don't have pixel, the row number 3.5, we don't have it, right? We have either row 3 or 4 or 6, etc. So since I have to work with the integers, there will be some errors. What I'm saying is that if I say this point P with red, let me try to show it with you like this black color, okay? Point P corresponds to this point P prime. If I draw these two lines, in the real world they may not intersect, because in three-dimensional world, two lines, and in two-dimensional world, yes, two lines have to intersect. I mean, the worst thing is that they can intersect at the infinity. We know that. But in the 3D world, two lines may not intersect. Okay, so what are we going to do now? I mean, I said that this point P corresponds to point P prime. They will not intersect. So maybe we can do this. Find the line segment that connects these two lines. Okay, the minimal line segment that connects these two lines, the shortest line segment that connects these two lines. These minimal line segment will be perpendicular to both of these lines, and find the center point of that line segment P, and that will be our real world point P. So here I am assuming that whatever I do, however I am careful in doing the camera calibration, in finding the correspondences, doesn't matter, because of some errors, because of the noise in the images, because of my lens properties, doesn't matter. These two lines will not perfectly intersect. So here I would do this. Find the line segment, that the minimal line segment that connects these two lines together, and find its center position. That's what I'm going to do. Okay, so I will use almost the same notation as the fundamental. Remember the essential matrix, how we derived it? We looked at this. We looked at this three vectors that are on the same plane, and we cross product them, etc. We are going to use the same kind of idea. This is what we are going to do. We are going to say that they did not sign it. We are going to say that, okay, we are going to say this. I will say, I know this line, this is our baseline, right? This red line. Okay? This is my baseline, and I know this one. From the baseline, I know how to go to that way, to the PR, it will go. From OL, I can do this one too. Let me try to do it like a line. I know this one too, okay? If I can get this line segment, then I should be done. Okay, so how am I gonna do that? It will be not that difficult. Let's try to write it together. So I know this one, OL or R. This is our baseline, right? T. Okay, that's kind of given. Also, I know the R between L and R. I know this one. PL and PR, I already found it. I know that they correspond to each other. So I am going to run this algorithm. Okay, all vectors and coordinates are referred to the left camera reference frame. So everything has to be in the left camera reference frame. So I need to translate this PR to the left camera reference frame by adding this R and rotating by this, adding this T and by rotating this R. Okay, so the input is formed by a set of corresponding points PL and PR. Let's look at this one. APL from here. Okay, what is PL? PL is a three-dimensional point, right? It's a three-dimensional point. If A is a real number, what is APL? A starts from 0 and it goes to infinity. A is like that. What is APL? What kind of thing it defines? Suppose A is 0. What does this make? If A is 0, then I would get what? If A is 0, let's say this PL is 3, 5, 7. If A is 0, then if A is 0, then what? Why everybody is just looking at me? Just say 0, 0, 0. So what is 0, 0, 0? OL, right? Okay, this is OL. So if A is 0, then I would get OL. What is A is 1? What if A is 1? If A is 1, you would get PL, right? How about A is 0.5? You would get this point, right? If A is 2, you would get this point and that point, right? So this is a line formula actually, right? So you change A from 0 to infinity, you get all these points on this red line. Okay? You get all these points on that red line if you change A from 0 to infinity. Okay? So that's how you represent lines in 3D world. Okay? In 2D world, AX plus BY plus C is equal to is a line, right? In 2D world. How about this one? AX plus BY plus CZ plus D is equal to 0. What is this? It's a plane, right? In 3D world, it's a plane. In 3D world, it's a plane. It's not a line. Writing line formulas in 3D world is not that easy, but I can write it this way. Okay? So APL it represents this line. And similarly, I am going to do this BPR, and it's going to represent this line, but it will be in the coordinate system of the right camera. Okay, but I like to represent it in the left camera, so I need to rotate that point using the R, and then after that I need to add this T. That's what I'm going to do. So let's go back here. Let APL be the ray L through OL. Okay, you understand this one? So when A is 0, it is OL. When A is 1, it is PL. And then for the right one, that is the yellow line, yellow ray, okay, I am saying that, okay, T plus B RTPR. RTPR is the rotated version of that PR, so I am bringing to the left coordinate system, multiply it with this new number B, and add it to T. So everybody is in the left camera coordinate system. Okay, so I have formulas for the red and the yellow lines. Okay, formula for this one is not that difficult. I know that one too, right? I know that one too. It is just T. Okay, so the tricky part is this one. How about the formula for this small line segment? Well, I know that this small line segment is perpendicular to both L and R, right? So both this red line and the yellow line. So what does that mean? If it is perpendicular to both of them, if I cross product these two lines, I can get the direction of it, right? I can get the direction of it. That's what I am doing. Okay. If I cross product PL with RTPR, okay, if I do that, I would get the orientation of W, that small line segment. Okay, that small line segment. And let's look at this formula. We say that if I write this APL minus B RTPR, okay, plus CPL cross product RTPR equal to T, that will be my formula for this whole thing. So it is kind of a loop. I will start from here, go there, go up there, come back, and like that. Okay. So for this one, I have APL A here, and here B, and at the center I will have C. Three unknowns, one unknown, two unknown, and three unknowns, and one equation. How am I going to solve this? I have one equation but three unknowns. And I don't have any other information about this system. That's all I have. How am I going to solve this problem? Three unknowns, A, B, C, but one equation. I need three equations. How do I solve this problem?
Other corresponding points.
Well, I am not going to solve the fundamental equation, fundamental matrix, or anything. I am trying to say that if PL corresponds to PR, what is the depth of this point P, or the XYZ point of this P? I am not talking about any other point, just one point, okay? I mean, if you are right, if I am going to solve for F or E, but I am not going to. I just have one point. I say that this PL corresponds to PR, and I am trying to intersect these two red and yellow lines. They don't intersect, and I wrote this equation. And it looks like I have a single equation, but three unknowns. How am I going to solve this problem? Look at the equation. Is it a single equation or many equations? What is the dimension of PL? How many elements does PL in it? It's a vector, right? It's a vector of size what? It's a vector of size 3, right? It's a vector of size 3. And PR is the same. This one is the same. This one is the same. This is a 3 by 3 matrix. Well, actually, this is a A times, okay, PLX, PLY, PLZ minus B times a matrix times PR. PR is 1, 2, 3. As you see, there is the top part of this equation, then the center part, then the bottom part, right? I have 3 equations actually here, okay? So solve these 3 equations with 3 unknowns, you get your ABC, and you solve your problem. All you need is just get APL and BRTPR, okay? You know these two. Once you know them, the center point of this PL and BR will be your solution. That's how you solve this algebraically, okay? That's good. Good. Any questions on this? But there is a problem with this approach. The problem is this. What if I have another camera looking at the scene like this, and this is the central projection, and I have the third camera, and that's the corresponding point in there? Well, I mean, if I have more than 2 cameras, this logic will not work because I don't have a complete loop now. What am I going to do? For this case, maybe I should not use this solution, but my solution should be something different. You remember this one equation? Okay, P times M, 1 over Z is P. That's our projection, right? And in our projection, I have intrinsic parameter, rotation matrix, and the translation vector. I have all of them, okay? So let's say I have camera 1, okay, and this is M1, and M2, and M3, and M4. 4 cameras are looking at the same scene. I have the correspondence between these 4 cameras, and using the 4 cameras, I like to find the real 3D point of a given point, okay? So let's say I have this point P, camera 1, camera 2, camera 3, camera, and camera N. They all do this. I know that, okay, this one, P1, P2, P3, P4, and P5, they all correspond to each other. I know their matrices, M4, M3, etc. Calculate the depth of, or the XYZ of this P. If I can do that, this would be much better than solving the stereo system for 2 cameras, because 5 cameras are better than 2 cameras. Why? Because they can see, I mean, I can eliminate the noise better. There will be no occlusion problems, okay? Occlusion problems will be as serious as the stereo case. Those are nice, but this solution will not generalize to this case. So what am I going to do? This is what am I going to do. I know this is what I know. Okay. I know P because for each of them they gave me P. They say that these points are corresponding to each other. I know that one. Okay. I know M value, and I don't know this P. Okay, and I don't know its Z value. I don't know those. Okay. This is a 3-dimensional point. I know that one. This is a 3-dimensional point. I don't know the values of it, but I know that this is a 3-dimensional point. So what happens if I do this? P cross product MP. If you cross product the same thing with itself, you would get what? Remember the cross product formula? If you cross product something with itself, you would get, remember the schematic formula? 0, 0, 0, A3, A3, A2, A2, A1, A1. This is minus, and this is minus. Remember this one? Let's go back. Okay, here it is. Okay. If these are all A's, this is A, I am cross product, I am doing this cross product between these two. So what happens? A3 minus A2, sorry, A3 times A2 minus A2 times A3, they will cancel each other. It's 0. A3 A1, A3 A1, yeah, they will take it out each other. So the answer is what? It is 0, 0, 0, right? If you cross product something with itself, the answer will be 0. So if I cross product this with MP, I will get 0. So that's nice. So what am I gonna do now? I will cross product P1 with M1, 0. P2 with M2, P, 0. Dot dot P5 cross product M5, P, 0. They all are producing the same 0. Let me make it smaller and put it in here. So I know this one, I know this one, this one, I know all of them. The thing that I don't know is these P's, and they are the same P. So that's good. That's good. Why? Because I can write such nice linear system. In this linear system, I have many P's, they correspond to each other. I have many M's, that corresponds to the matrices of the different cameras. And this P is common for all of them. And at the other side, I have 0. Okay? So it doesn't matter how many points you have that correspond to each other. You put one nice linear set of equation with 3 unknowns and solve it using the least squares. In this case, I need to use the least squares because only 2 cameras are enough for me to solve P, but I am including more points. That means what? This is an overdetermined system. Okay? Overdetermined system means that I should use the least square to minimize the error between the possible solutions. Okay? So this is a better algebraically defined solution than this solution here. This is nice, elegant, but this is algebraically more sound and it has the least square solution in it. Of course, for both cases, you need to know about the matrices, the projection matrices, or the camera calibration matrices for all the cameras. Once you know them, all of them, then you can get their depths in real world coordinate systems. Okay? So this problem is reconstruction problem. Reconstruction is you are given the corresponding points between the images, and the reconstruction will tell you the XYZ point of those. Okay? And it looks like I have this nice Opencv function, triangulate points. It says that give me the projection matrix of the first camera, projection matrix of the second camera, the points that you think that they correspond to each other, okay? Point set from the first camera and point set from the second camera. I will give you the corresponding 3-dimensional points. Okay? It says points 4D, but 4D means that I have an array of three-dimensional points. That's why it is 4D. Okay? So these triangular points will give you this one. Can I click on this? Maybe there is a nice example. I can't. What? Triangulate points. Opencv triangulate points. Yeah, nice. Good. Tutorial, that's better. Let's see if we have an example. Okay, input arrays, points to D, input array of arrays, projection. So this is much better, right? Array of arrays, that means that I can do the triangulation not only between two cameras but many cameras. So it is input array of arrays, projection matrices for each image. It has to be 2n. The input vector of 2D points, it has to be 2n, and the output array is 3n. Okay, what kind of a tutorial is this? Triangulate points? No, well, there is no, it looks like there is no tutorial. And this one is different. This one will take this one, yeah. This one will take many cameras, I guess. The one that I showed you will take two cameras, 1 and 2. Okay? Good. Well, I remember that there was a tutorial and there was an example about triangulation points. Maybe just an example. Yeah. Let's see the example outputs. Yeah, it just runs it, that's it. Triangulation. Call the triangulation points and returns it. It doesn't visualize it. Sorry, I couldn't find it. Anyway, that's how it works, and that's the basic reconstruction formula. Okay, any questions? Then I will continue if you don't have any questions. Rectification. Without the epipolar geometry, our job of finding the correspondence wouldn't be that easy. So what are we going to do? We will use the fundamental matrix to find the corresponding line. I have camera number 1, camera number 2 images. I have a point P. Okay, find this corresponding line and make your search on this line to find the corresponding point for P. That's our plan for now. But some people say that, why don't we transform these images in a way that, the corresponding points are always at the same line. For this any point on this line, the corresponding points will be on the same line on the other image. So I don't have to calculate any epipolar lines. Okay? It is exactly the same line. This is called rectification. It's something like this. Okay? These are two images of the same scene, stereo pair. Let's look at this point here, this point. Okay? The corresponding line for that point is this line. Okay, let me try to make it a little bit darker. Okay, so that line. So it is not a very convenient line, because I need to write a line formula and follow the line formula to find the corresponding points. But if I transform these images such way, this, okay, so I have two new images now of the same scene. I am not taking new images of the scene. I am just transforming this image to this image to this image. So any point on this line, its correspondence will be on the same line. Doesn't matter where you look at it, on the same line you have your correspondences. Okay? Previously it was different. Okay? So that's the nice thing. If I can rectify my images like this, then I don't have to use the fundamental formula for each search. My search will be very, very easy. That doesn't mean that I am not going to find the fundamental matrix, because this rectification is done using the fundamental matrix formulas. And this is how it is done. Let's say, just a visualization. Let's say I have my cameras. Camera number 1 is this blue one. Okay, or maybe the blue one. This is the blue one, camera number 1, right? And the corresponding camera in the other part is this one. Okay, and I know that this point here corresponds to this point, and these are the conjugated epipolar lines. Somebody says that, why don't I transform this image into an image like this, a virtual camera like this virtual camera and this virtual camera, they see the same scene, but instead of seeing it in like here, it will see it here, and instead of seeing it like here, it will see it here. Okay, so I can run my correspondence algorithms on the green images, okay, not the blue images but the green images, and that will make my correspondence finding job a lot easier. Okay, so basically it is this. So red image and the blue image, if I rotate these images in a way that the final corresponding epipolar lines are horizontal and they correspond to each other, this procedure is called rectification. Okay, this process is called rectification. Okay, it can be implemented by projecting the original pictures onto a new image plane. That's nice, and this will make our depth estimation procedure a lot easier. Good. So for the rectification, of course, Opencv has many procedures, and can I do that? Can I Opencv stereo rectification? Yeah. Let's look at the documentation. I see lots of rectification stuff. Maybe rectify. Yeah, rectify and calibrate it. What does it say? Okay, give me the left points and right points. Give me the fundamental array, fundamental matrix. Okay, and you tell me what this H1 and H2 are. Okay. Can anybody tell me what this H1 and H2 is? What? It doesn't take any images. Does it take any images? It takes point 1 and point 2, corresponding points, and it takes an input array fundamental matrix. It takes the image size, and it outputs H1 and H2. Well, I'm not giving you any clues here, but you are supposed to know this. Yeah, 2 homography matrices. You are going to apply this homography matrix to your first image. You are going to apply this homography matrix to your second image. That will rectify your images. Remember, what does the homography do? If this is your, oh, well, I cannot draw it here, right? If this is your image, if you pass it through this homography matrix, maybe it's going to be like this, right? Rotation, skew, and that kind of stuff. That's what happened here, right? I applied this homography, get this, and you see it is rotated, it is skewed a little bit, and this part doesn't make any sense for the other image. I lost some part of it, but it is rectified. Okay? So that's how it works, and let me show you the rest of it. I don't know about this threshold. That's probably some algorithm dependent. Optional threshold used to filter out the outliers here. Okay. Output rectification homography matrix, 3x3 matrix to be applied to your image. Okay, so rectification is here. Good. Okay. So this 3D reconstruction problem, if you know everything, if you know your R matrix between 2 cameras, if you know translation vector between 2 cameras, okay, that means you know both intrinsic and extrinsic parameters, then you can solve the reconstruction problem, no problem, okay? But if you know only the intrinsic parameters, I mean your left camera and right camera, you don't have the extrinsic parameters R and T. You know only the intrinsic parameters. You can reconstruct your scene up to a common, okay, scaling factor, okay? So I can give you the depths of XYZ values of each point, but you are going to multiply whatever I give you with a number, with a constant number for the whole scene. That's an unknown scaling factor. All the points that I give you, P2, P4, whatever, you are going to multiply it with a K. I don't know what that K is because you didn't give me the extrinsic parameters. Okay, so maybe it is easy to find this K. Why? How? If I know the length of something in the scene, okay, I do the same measurement with my P values. Subtract the P values of the ends of that thing, and calculate the K value, and you know the K value. Worst thing is this, okay? You have only the correspondences between left and right image and nothing else. I don't have K, I don't have R, I don't have T. Of course you can do the stereo, you can calculate the fundamental matrix. You can get a disparity map between right and left image. But how about the actual depths, XYZ values? Say that I can give you your P1, P2, P3, XYZ values up to Pn, but you are going to multiply all of them with a projective transformation like a homography. Okay? So you are going to multiply it with this homography, and that will give you the real P values. Okay? So I'm not going to again go into details of these. I am just telling you the final results for the reconstruction. Good. Any questions so far? Okay, if there are no questions, maybe I should continue. Maybe I should give you some example about human stereo. We kept talking about human stereo, but we say that it is similar to human stereo, etc. But in fact, in human stereo, our eyes don't behave like fixed cameras. I mean, I have a point P in the real world. This is the left camera, and this is right camera. This is my projection P, and this is my projection P prime. This is PL and PR, right? If I change this point, if I make it here, it's going to be like this, right? So these will be my points. For the human eye, it doesn't work that way, okay? Because we keep moving our eyes, our eyeballs, right? If the things are close to our eyes, we cross our eyes and we do this thing. And if I bring it too close to my eye, I can't focus it anymore. Okay, I can't look at it anymore. If I am looking at faraway objects, our eyes become like parallel cameras. But if the objects are nearby, our eyes kind of cross each other, and they produce this kind of a scene. So it is difficult to have a camera calibration system for this one. Because why? Because to look at your nearby objects, you change your focus by adjusting the lens. So your intrinsic camera parameters are changing. Also, you are rotating your camera too. Okay, so extrinsics are changing too. So the only thing that remains constant is your baseline. It's like 55 millimeters or something like that. Okay, so how is it going to work? They say that it works this way. If the eye orientations are fixed, okay, their principal axis will intersect at some point here. Okay, so if there is an object in your vision, well, by the way, for any point on this circle, there is a circle, right? Any point on this circle, if you look at any point on this circle, this angle will not change. It will be the same thing. It's called the Müller circle. Okay, on the Müller circle, this angle will not change. The angle between your left and right eyes, the principal axis, will not change. While you are looking at anything on the circle, any point outside the circle, there will be an angle D. Okay, this angle will be, of course, smaller than this F. If you are looking at any point inside the circle, and it will be like this, and of course this angle will be larger than F, right? So what I am saying is that your disparity doesn't come from the difference between the position of the images on your left and right eye. The disparity comes from the difference of these two angles, or these two angles, D minus F. That's the disparity. If disparity is 0, that means that you are looking at something on the Müller circle. If disparity is like this, D minus F, negative, then you are looking at something outside the Müller circle. That's how the human eye camera system works. Okay? Any questions? I think I'm going to talk about this a little bit more, but no, I think I will come to this later when we talk about these kind of cameras. Any questions? Well, okay, let's take a break then. Let's be here around 16:38 again. Herkes bunu imzaladı değil mi arkadaşlar? Nerede bu? Okay, so let's look at this. Instead of doing the human stereo, go back to our regular stereo with the parallel cameras. So there is no camera movement. Cameras are fixed, and we have a short baseline. That means the distance between left and right is very, very small. Remember our formula? Our formula is Z, the depth is equal to F times T over D, right? So T is the baseline. Question for you, what happens if T is 0? If T is 0, then in that case maybe my left camera is going to do this, right? My left camera, and my right camera is going to do this, or maybe I shouldn't. Okay, this is my left camera. It is seeing this. Okay, this is my left camera, and this is my right camera, and this part is the common field of view. Okay, in this case, this is the common field of view, left and right. This is my common field of view. If the baseline is 0, this will be my common field of view. But looking at this formula, it says that if T is 0, then all the Z values will be degenerate values. Okay, they will come back as 0, 0, 0. That means what? If the T is 0, there is no stereo. Okay, you cannot do stereo with T is 0. Baseline has to be greater than 0. When you get close to 0, the baseline becomes 0, you are going to make more errors. When T is very, very small, you are going to make lots of errors because T is small. I mean, disparity is calculated, right? You calculate your disparity from the images. If you make a smallest error in calculating D value, since T is very, very small, your Z will get affected a lot. That's why we say that if the baseline is short, okay, we have a nice common field of view, okay, but our large depth errors will be the problem, okay. That's the problem with the small or short baseline. Get the cameras together, and you have a large field of view that is common to both, but you will have large depth errors. So make the baseline large. If you make the baseline large or longer, this time your field of view will be, common field of view will be very, very small, okay? So your left image and right image will overlap at a very small fraction. That will be a problem, but your depth estimation will be better. Also, there will be occlusion problems too. What's an occlusion problem? I mean, since your cameras are far away from each other, let's say one camera is here, the other camera is way over there, right? They are seeing the same scene, but one of them sees these desks from the left side, the other one sees the right side. They are not seeing the same object. They are not seeing the same part of the object. So that's not going to be good. So some people, they say that, why don't we do this? Do this, okay? Make the left and right separated, long baseline, but rotate each camera so that their principal points are converging to each other. Okay, these are the converging These are called the converging cameras. Okay, so we kind of prefer this kind of a configuration. So with this stereo, with the converging cameras again, we have the holopter or the Miller circle, and these angles will play roles in this case. But I think I will skip this part because I already talked about it. In reality, we don't use these kind of setups much. I mean, even if you do it after the rectification, all you do is just looking for the correspondences. So I'm going to skip this part until I get to the correspondences. Okay, so from the beginning of this chapter, I kept talking about finding the correspondences, but we never looked at the details of it. So usually, if you have two cameras, let's say this is your point P, this is your camera number 1, camera number 2, this is central projection, okay, this is PL and this is PR, okay. So what are we going to do? We say that maybe we will have the camera matrix M1, camera matrix M2, we have all of those, and we have our rotation and the translation matrices and everything, and we know the correspondences, and we can calculate the depth. We said that kind of stuff. So find the correspondences, feed all this correspondence information and the matrix information into our formulas, and you will get the XYZ values of this P. That's what we do. But before we begin to do anything, we need to find the correspondences. That's what we are going to do now. First, we are going to assume that our images are rectified. So on this line, all the correspondences will happen, and any point on this line will be at the other image. You don't have to look at anywhere else. Okay, see, the corresponding point for this red is here, this one is here, this one is there. It is always on the same line. So rectification is done. I don't care about the fundamental matrix anymore. I don't care about the matrices anymore. I am looking at the images, purely image processing thing now. Okay, it's about stereo, purely image, image-based stuff now. So let's look at this problem. How do I know? Let's say I like to find. I like to find the same window on the other image. Okay, is it this one? Is it this one, or that one? Okay, I need to make a search on this line. So when I am doing this search, what am I gonna look at? Let's look at some of these possibilities. Let's say I have 5 by 5 window on this one, or like this. Is it 5 by 5 now? Anyway, let's say maybe 7 by 7. Anyway, so 7 by 7 window here, and I like to find the most similar window on the other image. So maybe is it this one, or is it this one, or is it that one? So the simplest thing you can do is, let's say this is window left. On my window left, I have X and Y values for each one, and on my window right, I have X and Y values. So what would you do? Maybe I can do this: window L, X and Y, minus window right, X and Y. Okay, if you subtract them, and if you add them together, I like this value to be minimal. Okay, minimize this value. What's going on? Okay. So I like this value to be minimum. So, well, maybe I should take the absolute value of it, right? Take the absolute value of this value and add them up, and this is what you're going to get. Okay. Find a window on the right image that will minimize this this summation. Okay, so that's one thing. Comparing windows, I can compare F window, G window, subtract the corresponding elements and add them up together, and whatever minimizes this, should we close the windows maybe? Okay, just subtract these windows and that will be it. Okay, so do you like this? How about this one? What does it say? What does it say? It says find the maximum difference between these two windows, right? Okay, say that. Okay, look at this part and look at this part, take the difference and do the same thing for all the corresponding ones and find the maximum one. That will be your similarity. This one says that find the differences between all the corresponding elements between these two windows and add them up. Okay, good. Or somebody else says this: subtract all of those, take the squares of it and add them together. This one is called SSD, sum of square distances, sum of squared differences. This is sum of absolute differences, SAD, sum of absolute differences. Okay, this is SAD, and which one do you think is better? This one or that one? Or are there any difference maybe? Are they the same thing? This one says that choose the window of all the windows, choose the window that minimizes this SAD value, or the other one says that choose the one that minimizes SSD value. Which one would you prefer, SAD or SSD? Why? Who said SSD? Why?
It has bigger differences because
yeah, SSD says that I don't like the bigger errors, right? Because if there is well, I shouldn't say error, but the difference. If there is a difference between two pixels like 2, that will penalize it with 4, but this one will keep it as 2. And if the error, if the difference becomes like 5, it will be like 25, right? So this one doesn't like very large differences. Keep the differences small. This one says that, well, large differences are bad, but I mean they are as bad as how large they are. This one says that they are like I will multiply each difference by itself. It is too much. So sometimes this works good, sometimes this works good. The nice thing about this one, I can take the derivative of this one. Sometimes I need it. This is not a differentiable function because absolute value is not differentiable. Okay. Another one is this one. This is called cross correlation. Multiply the values with each other. Well, it's kind of. By the way, you maximize this one. You minimize this one, minimize this one, minimize this one, and maximize this one. Then can you see the logic? Two windows are similar if the pointwise multiplication of each element is the summation of the pointwise multiplication of each element is largest. Can you see the logic? Why should that be? Do you guys remember this problem from your calculus classes? Which shape, I know the perimeter of these shapes are the same. Let's say it is PE. Let's say the perimeter of this shape is 10. Perimeter of this shape is 10 too. And perimeter of this shape is 10 too. Which one has the largest area? The square one, right? Square has the largest area. It can be proven, right? It can be proven. So this one kind of has the same idea. I mean, multiply these pixels if they are similar to each other. That will make this multiplication the largest. That's the idea of the cross correlation. And we are going to see that these are very, very related to each other. Minimize this one is equivalent to maximizing this one, and we are going to see. And well, let's get it. Let's get this one. Let's open this up. It is f squared. It is f squared minus 2fg plus g squared, right? We say that f and g are images. I mean, they are not talking to each other. Let's ignore these two. Let's ignore this one, and let's ignore this one. All I have is minus 2fg, f times g. So minimizing this one means that minimizing this, so fg has to be as large as possible. So that's what it says actually. I mean, these two are kind of the same thing. So cross correlation and SSD are two popular comparison stuff. So what are we going to do? We will take this window. We will take this window here. On the same line, corresponding line. Okay. On the same corresponding line, we will check each window one by one. Okay, we will check each window one by one and run one of these SSD or cross correlation or the sum of absolute differences algorithm, and choose the window that minimizes one of those metrics, and hopefully you are going to get this one. And that will give you your correspondence. Once you have your correspondence, you have your disparity. Once you have disparity, you can calculate this f times t over d, your depth value. Or from the disparity again, you can calculate, given the disparity, you can calculate your projected 3D points. Let me see if Opencv has from disparity to, okay, Opencv stereo disparity to 3D, yeah, good. Okay. Depth map from stereo images, camera depth perception, well, disparity to points. Reconstruction from disparity, yeah. Depth map from stereo images, maybe. So what I'm saying is that if you have the, okay, this is the thing, yeah. Z is, we already know this one. There is a disparity image, and this is the corresponding one. Imagery, disparity show, compute, so it computes the disparity. But what happens after disparity? Couldn't find it, sorry. There should be a function given the disparity and the camera calibration parameters for a stereo pair. It gives you the 3D points. Okay, there should be a function like those, but I couldn't find it here. Anyway, what I'm saying is that after doing this, you calculate your disparity. Either you directly estimate your z value from the disparity, or you call that Opencv function along with your camera parameters, and you will get your XYZ values of those. Okay, So that's the correspondences. But the thing is that your left image and right image doesn't have to be taken under the same condition. The cameras are different. First of all, there is the noise difference between left and right, right? There is a noise difference between left and right. That's one thing. Maybe I can't do much about the noise thing, but your left camera and right camera are two different cameras. Maybe one of them is slightly darker than the other one. Human eye is so good at compensating these dark and bright images. We see the same thing. But for SSD or SAD, if there is a difference between left and right image in terms of brightness, maybe 10 level difference, it will mess up everything, right? So we don't like these kind of problems for SSD and SAD, okay? We don't like these kind of problems for SSD and SAD because these are all brightness dependent. These are all brightness dependent. I bet if I increase the brightness of this image by 10 gray levels up, and if I lower this a little bit, none of you will realize that these two images have different brightness values. Okay, you don't realize it. You will say that, oh, okay, these are the same images, and I can find the correspondences. But if I do that, these will fail miserably, and that's not a good thing. Let's try to find a good solution. How would you solve this problem then? If there is a brightness difference, overall brightness difference between left and right images, how would you solve this problem? Yes? Kind of a normalization. Take the mean and like distribute it like normally, maybe, yeah, we can do that. Normalization is kind of a solution, might be a solution. Yeah, why don't we do that, okay? So SSD is kind of, after the normalization of two and left and right images, take the SSD, that will work much better. That's why this is the most popular. And as I said before, these are closely related. But there is another method. It is called normalized cross correlation. It works this way. Let's say I have this window, 1, 2, 3, 4, 5 rows by 3 columns, okay? 5 by 3 window, okay? And on the right image, I have another window like this, and I like to see if these two windows are similar. How am I going to do that? I can do the subtraction of SSD, like this one, and this one, and then this one and this one, this one and this one, or they do this. Convert this to a vector, okay? So how many elements are there? There are 15 elements in there, right? So make this a one-dimensional vector of size 15. So this one will go here, right? This one will go the third element, and this one will be, I guess, here, and this one will be there, right? So I converted this to a 15 element vector, and I converted this to a 15 element vector too. So I have two vectors in 15 dimensional space. I normalize them. I make their lengths 1.0, both of them, and I measure the angle between them. How do you measure the angle between two vectors? What is the angle between two vectors? It's the cross product, right? It's the length, okay? Two vectors, V1 and V2. Okay, you take the V1's length, you take the V2's length, and the cosine of the angle between them. That's the definition of it. So the cosine, the cosine of the angle between these two vectors, if these two vectors are the same, this angle will be 0, right? If one of them is bright than the other one, then it will be longer, but the angle between them is still 0. If one of them is darker, again, the angle between them is 0, but one of them will be darker. That's what we are going to do. So the formula is this: take this one, two vectors, try to measure the normalized angle between them. That's called normalized cross correlation. This is the formula, okay? It says that multiply each one. So this is the cross correlation, one by one, but normalize it with this value. Normalize it with the squares of the each element, the addition of it, on the left image, left window and the right window. Zero mean normalized cross correlation. This works best, okay? This one will do the normalization per window basis. Okay, this one will do the normalization per window basis, and it works very well. Of course, it is more expensive than this one or that one. I know that one. Okay, it is more expensive than both of them, but it works the best. Again, see, this one is. By the way, nice thing is that about this one is it changes, the values changes from -1 to +1. Okay, +1 means that it is the most similar, it is the same thing. -1 means that it is just the opposite of the image. 0 means that they are not correlated at all. So this is nice. There is no maximum for this one or that one, right? The minimum is 0, I know that, but nobody will get 0. But what is the maximum? What is the worst case? I don't have the worst case. Worst case depends on the size of the images and the intensities and etc. That's why we like this 0 mean normalized cross correlation. Okay, and Opencv has many algorithms to calculate the disparity. You just give the input array left, input array right, left image, right image, and you give the output array as a disparity, and it will calculate the disparity and it will give it to you. But the thing is that, see, this is a pure virtual function. There is a hierarchy here, okay? There is a stereo matcher. There is a stereo matcher base class. You derive classes from that one. This compute disparity function is a pure virtual function. It is not implemented in the base class, but it is implemented in the derived classes. One of them, for example, calculates the disparity using SAD. This one calculates using SSD. The other one calculates using dynamic programming and etc. Let me see, can I click on it? Can I click on, how come I can't? Okay, I will write it here. Opencv stereo disparity and computation. Yeah, that one from stereo images. Am I getting the same thing? So this is stereo compute. Stereo is CV that stereo create number of disparities, block size. No, I need to find this. Get this one out. Let me go to the tutorial. Yeah. So the stereo matcher is the base class. Stereo binary BM and stereo SGBM. I forgot there. Can I click on it? Yeah, okay, good. So block matching algorithm. So it is matching the windows block by block. So binary BM. Let's look at the settable stuff. It is create disparities, block size is 9, so it is 9 by 9 windows, and I can filter lots of stuff. Uniqueness ratio, pre-filter, aggregation, binary kernel type, the kernel filter. Where is the similarity texture? Couldn't find it any. normalized response, and the user Sobel, okay, binary kernel type, aggregation window size, where is this? Oh, okay, stereo, okay, sure. Yes. Block, min disparity, max disparity, min disparity. How about this algorithm thing? Default, save. No, I couldn't find which method it uses now. Let me go to the other one. Oh, okay. Using block matching has introduced to contribute to Opencv by this. They have implemented their own technique here, and I don't know what do they have any algorithm specification here? No. So this is not, I don't remember this one. This is not, it looks like this is not using the window matching, it is using, how about this binary SGBM? Okay, so I have a GBM. Single pass consists of the 5 directions of 8 blocks, not individual pixels. I don't remember this either. I don't remember this paper. It is 115, right? Was it 115? No, 113. Semicolon matching and mutual information. Yeah. So it is matching. So it doesn't do it locally. It is more advanced than I told you. Well, this is gone. I cannot reach this one. So both of those methods are not as simple as the method that I showed you. It is not based on just local SSEs and local local normalized correlation. It is using more often. So the method that I told you is choosing these windows based on just one local description. It doesn't say, for example, let me show you this one. Let me show you. Get away. Yeah, let's get this one. If I am looking at an object, like this, a circular object, I have 3 points A, B, and C. This is how I see these points, C, B, and A. C, B, and A. Of course, depending on your point of view, see the difference between C and B is small. Here it is large, right? And the difference between A and B is small. Here it is large. This is expected if you look at real-world objects like that from different angles. But the thing is that you don't change the order. It is always ABC, ABC. If you don't have the surface discontinuity, if you have surface discontinuity like this, okay, here I have ABC on this object and I have D on here. This is ABD, this is BDC. So A comes from B and D. Here D comes before B and C. Okay? So order kind of changes. C and B order changes. That's what I'm saying. If there are discontinuities like those methods, they use this kind of an information. Okay? They say that I assume that on this part of the image there are no discontinuities. On this part of the image there are discontinuities. And I am enforcing these kind of constraints too. Okay? So if I can go back let's go back and let's look at this one. Okay, if I have calculated the disparity for this one, okay, and I found that the corresponding element is here, and for the next pixel here, the corresponding pixel should be to the right of that the previous correspondence. Okay, so I should remember what I have decided before, what kind of decision I made, and I'm going to make my decision accordingly. And after doing that, why don't I do the same thing from right to left again? Calculate the disparity for this one, make a search on this image, okay, and I should get exactly the same thing. If I don't get it, try to figure out kind of the middle way in between. So those two algorithms, they consider these kind of constraints too. That's why they said it is a global, semi-global calculation. It's not perfectly global, but semi-global. What does that mean? I am not just making my decision based on one window comparison. My decision will be based on comparisons with many windows. Okay, and enforcement of this kind of keeping the order relationship, also keeping the constraints between these two images from left to right or right to left. Okay, so those are, as I said before, those are more complicated than what I told you. It looks like they have changed their documentation. It wasn't like this before. But whatever they are, all you do is you just get a new object, stereometry object, and call this function compute. And whoever implements this stereometry, it's a pure virtual thing, they will implement it and you are going to use them transparently without knowing what's going on actually. Okay, good. Any questions? So far for the correspondence, our task will be correspondence from the rest of the chapter and until the end of the chapter. We started talking about the correspondence. These are block-based corresponders. Remember the Opencv talks about it? I'm not trying to match a pixel to a pixel. I am trying to match a window to another window. Okay? So if you say that if I make my window very small, like a 1 pixel wide window, well, you could do that, but that's not a good idea. Why? Because there will be many similar pixels in the other image. Okay, what are you looking for? A pixel of value 255? Well, there are many of them in the other image. So looking for a window that is most similar is a good idea. These are the block matchers, and we looked at the block matchers, and the Opencv, the base class says that it's a block matcher method, right? BM, block matcher method. Block matcher methods are not the only methods. There are other methods, and the other methods are feature-based methods. The idea is this: why do I have to calculate disparity for each pixel on the image? Okay, why do I have to do that? I will calculate the disparity or the depth only for certain pixels. If I know that that pixel is reliable, I will calculate the disparity for it. For example, this is my left image, this is my right image, okay, and I rectified them. I know that this line corresponds to this line, okay. I run sift or surf point detectors, and I have many points on this one, and I have many points on this one, right? So surf will give you the point descriptor. Get the point descriptor for this one, 128 dimensional vector. Get the point descriptors of each of these and find the most similar descriptor, and you say that for this point this is the corresponding one. Well, obviously this will not find a corresponding point for each point on the line, But whatever it finds is a nice one. Why? Because surf is a nice way of finding corresponding parts on different images. And on top of it, I have this epipolar constraint in my hand. Okay? So these are called feature-based methods. Similar to correlation-based methods, block-based method I did it before, okay, as before. But I only search for correspondences of a sparse set of feature images, not for all the pixels. That's why they will not have nice disparity images like this. Okay? This one calculated the disparity for each pixel on the image. Well, almost all the pixels. For example, this part is not calculated, right? Why do you think that these parts are not calculated? For example, this part is not calculated here. And what else? Maybe this part is not calculated. This part. Why do you think those parts are not calculated? Because there are occlusions for those parts, right? There are occlusions for those parts. Or also maybe there are some difficulties. Maybe the light is too dark in those areas. Maybe the features are not matchable, okay? I mean, especially this part, right? I mean, it is all the same color. How am I gonna choose the right one? So back to our original. I mean, why did I come here? I come here to show you this is a nice disparity image. How come I can't? Okay, this is a nice disparity image. I don't have to calculate those nice disparity images. If I am doing a robot navigation, I don't have to know the depth of each point. If I know the depth of the edge points of these desks and the chairs and the door frame, then as a robot I am fine. As long as I don't hit those edge points or the corner points, I should be okay, right? I don't have to find the depth points of all the image points. That's why for those kind of applications, feature-based methods are more preferable. So next week I am going to look at these feature-based methods, and I will finish up with this chapter of stereo. Okay, that's it for today, and I'm going to see you next week.